Hi, everybody. This is the lesson for Math 2, Wednesday, September 8th. Wednesday, September 8th. So, the first lesson in Math 2A for this semester. Okay, as always, make sure that you're following along. Don't just listen to me, don't just watch me do this. I want you doing this on your own paper so you're getting extra practice. And you'll have something you can look back to later. All right, what is an exponent? Exponent is a number that tells us how many times to multiply the base. For example, let's say we had 3 to the 5th power. How we say this is 3 to the 5th power. So in this example, the 3 is our base, the 5 is our exponent, and what it means is we're multiplying 3 to itself 5 times. So 3 to the 5th power, what this actually means is this: 3 times 3 times 3, 5 times. And of course, we could figure out what that actually is. So multiply that out in your calculators. It looks like 3 to the 5th power is actually equal to 243. So here's what will be covered in this video, in this lesson: the product rule for exponents, the quotient or division rule, same thing for exponents, and negative exponents, and zero as an exponent. So these 4 subtopics, working with exponents with these 4 rules. Okay, so first rule up is product rule, and we'll formalize it in a minute. Let's look at an example first. So say we had 3 to the 2nd power times 3 to the 4th power. So to figure out how to do this, start by using the definition of the exponents and expand each one of these terms. This is 2 terms being multiplied together. The first is 3 to the 2nd. The other term is 3 to the 4th. So if I expand each of those, what do we get? Here's my 3 to the 2nd, 3 times 3. And then here's my 3 to the 4th. 2 threes, right? First term expanded, and this is that second term expanded. How many total 3s are there? 6. So essentially what we're doing is regrouping. We broke these down into like an expanded spread out form, but now I'm regrouping it back as one term, 3 to the 6th power. Look at the exponents, how it started. We have a 2, we have a 4, and then look how it ended. A 6. So what's the relationship that you notice between 2, 4, and then ending with that 6? So a couple things I guess it could be, right? It could be going up like 2, 4, 6, 8, but you might notice that this number, the 6 that we ended with, is the first 2 added together in this case. So we had 2 3s, 4 more 3s, put them all together, it's a total of 6 3s. So how we can write that is 3 to the 6th power. Here's the product rule formalized. Two powers are being multiplied. When the bases are the same, and that's important, when the bases are the same, we can simply add the exponents. That's what we saw in the last example. So example 2, 5 to the 7th times 5 to the 3. So my product rule is telling me that I can add those exponents. So this should be 5 to the 10th power. Remember, the first term is a group of 7 fives. Next, we have a group of 3 fives. So how many fives are there? There's 10. That's where the product rule is coming from. It's a shortcut that allows us to just move through the problem quicker instead of expanding it like I did for the first example every time. Now, we're going to be working with mostly numbers and math that isn't just actual numbers. We're going to be using variables. Variables like X, Y, A, B, C, H, I, J, any letter. They stand for an unknown number. So X, when you see it in a math problem, it's standing in for an actual number, but we don't know what it is yet. So that's why it's called a variable, because there's some variation. It varies as to what number that actually is. It may have one solid value, or maybe it could stand for anything and we can plug anything in for it. It just depends on the problem. In any case, we're going to treat variables like we do numbers. So how can I simplify this problem and combine it into one term instead of two terms? X to the third power times x to the 12th power. Well, how many x's is that total? This is a group of 3, and this is a group of 12. So this is equal to x to the 15th power. That would be our answer. Okay, now we see something a little different. We see a negative exponent. Weird. But we know that we should treat our variables and our exponents the same way we do normal numbers, right? So to combine these, a to the 10th times a to the negative 3, if I add those two exponents, we have a total of a to the 7th power. Again, negative exponents. Treat them the same way that you would if they were positive. We're going to add the two exponents with that same base at the end. So 8 to the negative 5 times 8 to the negative 10, 8 to the negative 15 power. We'll talk in a little bit about what to do when we have negative exponents, but for now, this is good. Okay, 5 to the third power times 7 to the 6th power. Can I combine these together? No. They're not the same base. 5 and 7, right? Obviously, those aren't the same number. Now, remember what these mean. So if I were to expand this means 5 times itself 3 times, and then 7 6 times in a row. So here's my actual math problem. I can't group all these together because these are a different base than these 5s and 7s. Can't mix. So what we could do is figure out what 5 to the third is and multiply it to 7 to the 6th, but we can't combine these into one term. So for our purposes, we're done. There's no real simplifying to do here. Let's look at the quotient rule. So just remember the quotient rule. Another name for that would be the division rule. Same thing. When two powers are being divided, we can subtract the top exponent minus the bottom exponent. So let's try this out, and then let's look at why this works. So example 1 here, a to the 5th divided by a to the 2nd. Remember, a fraction is a division problem. So we could think of this as a fraction, but at the same time, it's also the top being divided by the bottom. So the rule says we can subtract the top exponent minus the bottom exponent. So that means this is equal to a to the 3rd power. 5 minus 2 gives us 3. Let's see why this works. Let's try the problem again and not use the rule, but just use the definition of an exponent. So on the top, we have a to the 5th. That means a times itself 5 times. In the denominator, we have a to the 2nd, so that's 2. Now remember, another rule from early in your math career is that any number divided by itself is equal to 1. So examples. 2 divided by 2, that's 1. 100 divided by 100 is also 1. Anything divided by itself. So any number, x divided by itself is 1. So back to our exponent problem, notice that we have a over a right here. So a over a, that cancels out to a 1. I'm going to cross those out. A over a again, those can cross out. No more, there's no more on the bottom to match up with those left over on top, are there? So we're done. We can't cancel anything else further. We have 3 a's. How do I write that with exponents? A to the 3rd. So the quotient rule, the division quotient rule, is really a shortcut. So we don't have to do this expanding and canceling every time, but that's what's happening when we use the quotient rule. We're technically canceling out the matches of a's on top and bottom, or whatever the number or variable is that matches on top and bottom. Let's look at another one. So here we have d to the 10th power divided by d to the 8th power. Quotient rule says subtract top minus bottom exponent. So this is equal to d to the 2nd, or 2 power. Okay, let's keep using the rule. B to the 3rd divided by b to the 4th. Top minus bottom, so that's 3 minus 4. So this is b to the negative 1 power. We use the rule. This is correct. In a minute, we'll look at another step we can take to further simplify these negative exponents. But for now, this is good enough. That's our answer, b to the negative 1st power. Subtract top minus the bottom. Now this is confusing, or could be, because it's a lot of negatives. We've got 2 negative exponents to start with. So let's do this work on the side. We want to do the top exponent minus the bottom exponent. So that's negative 7 minus negative 3. Remember, another old rule from the beginning of your math career is minus a negative, like we have happening right here. So whenever we subtract a negative number, those both turn into positives. It's kind of similar to using a double negative in language. It cancels itself out, and it actually means the opposite of what it sounds like. So these turn into pluses. So we have negative 7 plus 3, which is negative 4. So our answer is c to the negative 4th power. Okay, now here's a better example of the kinds of problems we'll be doing. So we have many things going on here. 3 different variables at once, and there's division. So we have e to the 2nd times f to the 9 times g to the first divided by e f to the second, g to the fifth. So how I would encourage you to approach problems like this is to focus on one letter or one variable at a time. So here's what I mean. I want to look at just the e's, pretend there's no f's, no g's at all, cover those up with your hand, and just look at the e's. And this will be a little simpler to solve. So e to the second over e. Okay. So the rule is do the top exponent minus the bottom exponent. What do we do when there is no exponent for a letter or a number like this? We treat it like it's a 1. So I'm going to add in a 1. Now, why do we do that? Because what does the exponents mean again? It means how many times to multiply something to itself. So e to the first power literally means e times itself 1 time. I'm not going to write a second because that would be e to the second, right? I'm not going to write another e. So these are equal to each other. So whenever you have just a number or a variable by itself with no power, no exponent, you can you can put a 1 there and treat it like it has a 1 exponent. Okay, back to our problem. So this is top minus bottom. So 2 minus 1, that is e to the 1. Or as we just talked about, that's actually equal to e. So I'm going to kind of write my answer below as I simplify each of the variables one at a time. So here's my running total for the answer. We just got plain old e. Let's do f's. F to the 9 over f to the second. Top minus bottom is f to the 7th. Bring that over to our answer. F to the 7th. Now the g's. We've got g to the 1 over g to the 5th. 1 minus 5, that's negative 4. So g to the negative 4. Okay. And there's our final answer. Now, we're going to talk about two last topics, exponents of 0 and exponents that are negative. We've been seeing some negative numbers as exponents. They are legitimate answers, but there's one more step I want to show you to kind of clean them up fully and make them as simplified as you can. Before we do that, let's talk about the exponents of 0. So here's what I mean. Let's say we had x to the 0 power. We've seen other numbers, right? What about 0? So here's our rule for exponents of 0. Anything to the 0 power is equal to the number 1. X to the 0 is 1. 5 to the 0 is 1. Okay, negative 20 to the 0 is 1. Everything to the 0 power is 1. Let me write that down. I want you to write it down too. Everything to the 0 power is equal to 1. To the number 1. In the next lesson, the next video, you'll see why that is. I'm not going to go into that now. I want you guys to just use the rule for today. And then in the next lesson, we'll talk about why this rule works. Oh, there it is. Main point. Anything to the 0 power is equal to 1. Very good. Now for negative exponents. So we've had several examples already that have negative exponents. And I have said that they are legitimate, like it's a legitimate answer. But it's just not as simplified as we can make it. So let's take an example. Like we've seen something like x to the negative 10. Now, here's what I want to show you first, and then I'll show you generically for for all numbers. So if we had x to the negative 10, this converts to 1 over x to the 10. So if you have a number, a base, being raised to a negative power, you're going to flip it. You're going to change positions and put it at the bottom of a fraction like this, 1 over base to the positive of that exponent. Notice that it changes. It's no longer a negative exponent. Here it is generically or generally. So let's say we had any number a to the negative b power. This is always equal to 1 over a to the b. Okay, you should notice that this matches up exactly with what I have above with my x example. Let me put a box around this. Make sure you have this in your notes. Also, by the way, all the examples should be in your notes, so you can look back at those and use them if they're helpful later. I think they will be. But you won't know if they are for you unless you try first. Now, this is a very confusing looking rule. I grant you that. I know. I understand. And again, I want to go into why this rule exists in the next lesson. So for today, I want you to just try using the rule. Tomorrow we'll look more as to like why this exists. One other thing I'd like to show you. Let's say that we had a negative exponent in the denominator to start with. So I'm going to do another example on top. Let's say we had 1 over, we'll say 5 to the negative 2. So how do I fix this? This becomes 5 to the 2. So the takeaway here is whenever you see a negative exponent, it changes positions. It moves either up or down, depending on where it starts, right? It goes to the opposite position. And then you can pay for that, so to speak, by changing the sign on the exponent. So we don't want to leave our answers with negative exponents. Earlier I told you that was okay and they're legitimate, and they are, but we want to clean them up and we want to have positive exponents whenever possible. So that means okay. That means that this in yellow would be the preferred answer, 1 over x to the 10 and 5 to the second on the right. These are both our preferred answers because they don't have any negative exponents. So whenever you see a negative exponent, the first thing that we should do is change its position and then change its sign. Main point at the bottom. Negative exponent means change positions, and let me add this in, and change the sign, meaning it's no longer negative. We're making it positive. Negative changes to positive. Okay, there is a homework assignment for this first lesson. It is 6 problems. Here they are. If you haven't already done this, then you need to do these 6 problems on paper. Do your best. You're going to simplify each one as much as you can until you can't change anymore, until you can't whittle it down and simplify it anymore, and then you're done. You're using the different 4 concepts from today's lesson. So on the first problem, we see a number times a number. So that'll be product rule. Again, product rule. There's a 0 exponent. That's important. We've got a negative exponent on number 3. We don't want to leave our answers with negative exponents. So convert that for me. What should that look like? Same for number 4. I want you to convert that negative and then simplify. Then we've got number 5 and 6, which are a little more complex, but they're nothing much different than what we saw today. So when you're done doing these 6 problems on paper, you take a picture, you email it to me. You should all have my email. All you got to do is search for Josiah in your Google, It's my name. Search for Josiah in your Gmail and you'll see it. Here's my email. Josiah Henderson at ofy.org. Thanks for watching. I hope that was useful, and I will see you in class.